Hello everyone. I hope you can hear me well. Super. So we will start with today's lecture, um, which is about fundamentals of the course. Um, so what we did last time was generally get an overview of why numerical simulations in metal forming are so important. And today we would like to basically connect our previous knowledge with the current advancements and how we will build on that knowledge. And today's lecture is all about that um, building that connection with the previous knowledge and setting up the ground for this current subject. So the general topic of today's lecture will be the fundamentals of this course. And again, you know that Professor Pral is basically the course course head, and Dr. Irani and me are facilitating him delivering the lectures and answering all the questions of the students and facilitating them. So we have already done with the introduction into the metal forming process and the numerical simulations lecture, and today we'll be talking about fundamentals of numerical simulation in metal forming. And you can see the rest of the breakdown here in these slides. Um, just before moving forwards, I already shared all the books and extra things. So let me just share this screen quickly here. Um, so if you will go in the learning material, you will be able to find all the books in this books section. If you will go back, the extra reading material, world steel in figures related to all the statistics which we shared in the first presentation are shared here. You can also find them on internet on your own. And then the lecture slides. So I already shared the lecture slides of the first lecture here for your reference. I also tried to, I recorded the first lecture. I tried to upload the recording, but it didn't go as planned because now I don't want to upload them on YouTube but rather on our own channel, for which the link is given here. So yeah, this one. The issue with this channel is that I do not have access of uploading videos here for now. But here you can generally find information about other courses. So for example, lectures on numerical simulation um, from the previous courses are already by Christian Schmidt are already present here, which you can go through and take a look if you're interested. So yeah, just a quick background on where the data is available for the reference of other students before we continue with the current lecture. Okay, so the lecture objectives for today will be to quickly go through the background of metal forming and then again the classification and types of forming processes. Just to make sure that the manufacturing processes are quite many, and we are specifically dealing with here in this subject, specifically in the specialization of metal forming, we are dealing with a very narrow niche of processes which we are dealing with. And then the metal forming is basically a very complex, detailed process or phenomena, and we to understand it and to model it, there have been certain advancements on the technical side, and they are basically covered in our different course, which is fundamentals of plastic deformation, and not here. So we will always touch them, but the fundamentals are discussed there, and here we are just using those principles and methodologies to further advance and model them and let the computer solve those issues. So in this lecture we will have a quick connection with those fundamentals of how the plastic deformation takes place, what are the basics there, and then after understanding this, we will move towards the different classifications and types of numerical simulation models, where we will generally go through different types, different approaches of modeling a process to give an overview of what are the different possibilities, what what can be done, and then we will also talk about basic material models and numerical solution possibilities, um, and in the end we will look at an example of the kind of information that can be obtained from numerical simulations. And there, if we will have time, we would like to watch a video together to look into the details of how the numerical simulations are done and what kind of results we can get from them. And in the end, we will conclude our today's lecture with components of the numerical simulation model. We will quickly discuss them in detail because that is what will help you keep um, uh, keep the bigger picture in mind when we will continue with the lecture, because from now onwards, Dr. Irani will take over and he will talk about different approaches of numerical simulation methods, so different kinds of approaches and solvers, and then mathematical equations and material models. And it is important to have a bigger picture in mind. So where do all those things come in, and why are you studying them, and what are they helpful for? So yeah, we will end our lecture with understanding the components of numerical simulation model, so you can make a bigger picture of the next lectures and where they fit. So yeah, we will start with the general, very broad classification of manufacturing processes. So manufacturing processes are basically, as we discussed in the last lecture, are the processes which are used to convert raw material, bulk steel. So we produce steel in the form of billets and very huge blocks, and then we want to convert it into the desired shape so we can manufacture different things out of it. And all these manufacturing processes are basically related to converting that big blob of steel or any material into desired shape or structure, which can then be used in the in a process. Um, so the manufacturing processes are generally classified into casting, forming. Um, these are generally the bulk deformation categories, where the casting is usually related to the material manufacturing after melting of the material and then resolidification in the desired shape. And forming is basically converting that material, shaping that material in the form of wires or sheets, or then converting those wires or sheets into desired shapes by applying loads in different directions. And then there is a material removal process, which is a very large field, which is related to removing the undesired material and then leaving off with the required material in a desired shape. And those general procedures are related to milling, turning, facing, boring, drilling, and nowadays more advanced machining of the same machining categories, but which are computer controlled milling, turning, and routering. Then we have a bigger category of powder metallurgy and additive manufacturing, which is nowadays coming, which is nowadays a very hot topic. So where we have powder of desired material, and then we can directly print it or press it in the form of a shape, or directly deposit it in the form of layers to develop different shapes. And then we have different finishing processes, where we take care of the surface finish or the smoothness of to make the material desirable. Or then we have different processes for polymers as well. For example, thermoforming, injection molding, and blow molding. So this is a broader category of all the manufacturing processes, and we will be only focusing on um, if I have a laser. So we will only be focusing on this part here. So the forming part. Rest is something which we will not be considering. Now I will not be able to move upwards. So now yes. And then if we go down into subcategory of forming processes, and this is something which we already discussed in the previous lecture, but just to brush up that knowledge, and maybe some new students are here to help them also get the picture, get the idea. The forming processes are basically divided into, can be basically classified by different categories, by different method, sorry, by different methods. Um, One of them is by defining the type of forming load which we will apply, and here the classification is based on that. So um, the forming processes can be classified in the form of compressive forming, where we are applying compressive load. These are the subcategories related to that. Then the forming processes can be classified based on the tensile compressive forming, where they are applied on certain different sections of the material, or they are applied simultaneously at different places. So deep drawing is one of the major types of formings here, and then we have other forming operations related to this category. And then there are tensile forming. This is usually not um, quite the bigger category, so most of the processes do not fall into this category, where we just apply a tensile load and shape our material based on that. And then there is bending forming, where we bend a material into the desired shape, and here basically um, this can be done by using a linear tool, by the rotary tool, or yeah. And then we have a shear forming, where we are shearing off the material, for example in the form of flow forming operations. So yeah, this is generally the broader category of forming operations. And if we want to categorize them further, there are other categories, but yeah, let's take a look at this slide first. Uh, this is so just remember that E is shear. I will put this here. hmm Just remember that E is shear, and I, A, B, C, D, E. Um, so when we talk about the first rolling process, this is profile rolling, where we have two rolls through which this red material is coming out. Here in all these figures, the analogy is such that the red is our workpiece, which is being formed into a desired shape, and then this blue is basically the tool which is shaping the material. So if I am using this process of rolling, what do you think is the applied form of load, A, B, C, D, or E, which is being applied here in this case? So I will start the poll here, and you can vote on what do you think is the right option for um, the process 1, which is rolling. Okay, interesting. So I see that two students have voted for option A, which is tension, and two students have voted for C, which is tension compression. It I would say it depends on the ruling process. So if it is forced ruling or it is free ruling, in case for now I can see that the two arrows here are just representing the rollers being rotated and there is no third forced direction here. So I would say that basically what it does is that the material is undergoing material is going through the rolls and load is only being defined in this direction, which shapes the material into the desired shape. So this is basically normal rolling is basically, oh, it is not writing really well, but normal rolling is generally um, related to compression. So almost 7 students answered this question. So yeah, um, that's great. It can be tension compression if there is an external load applied, but here there wasn't any, so yeah. Then I would like to ask again. So now this is a second process, which is um, deep drawing. So deep drawing is quite interesting because initially we have a sheet block, a sheet plane, and then we have a gripper, a die which is holding this sheet, and then we have a punch which is helping us to deform it into the desired shape or the cavity. So you see here half is sectioned as an initial shape and then sectioned as half is sectioned as an initial position and half is sectioned after the load has been applied or the die has been moved down. And what do you think this setup belongs to? This too. So I will turn on the polls again and you can vote again. So does it belong to tension forming? Does it belong to compression forming? Does it belong to tension compression forming, bending or shear? So one student answered that it is E, shear. Um, so here you see a specific category which is related to shearing, and shearing basically means when we are applying a load, um, when we are applying deformation such that oh, I have to turn on the pen. When you're applying load such that there will be a shear failure, um, and then we call it a shear. But here in this case, most of the students answered C, tension compression, which is uh, which is correct in generally in normal deep drawing process. Some students answered B, compression, pure compression. I don't see why, but some students said bending. Okay, interesting. Yeah, so there is a lot going on here. If I look at this area here, of course there is bending going on. But generally, what happens is we consider a sheet a 3D block because usually it is not 2D. And what we are doing in this 3D system is that within this thickness, the sheet is undergoing compression along the axis, and along this wall, the sheet is undergoing tension. So we are applying basically tension on the sheet, and due to this tension, the sheet is flowing into the cavity and is undergoing permanent deformation, and the compression is basically on the rim of the sheet. So that is why it is categorized as a tension compression category and not really bending. Bending is this kind of procedure where we have a 2D kind of space where we are just applying a bending load and the sheet is bending in a certain direction where there is no tensile or compressive load. And here you will see that this punch is just bending this sheet in this direction where there is and the related force is not related to the applied tension here. Interesting. So yeah, that was quite an interesting case. Helps answer other questions as well. And then we will come towards stretching. So then here we see that we have one fixed gripper here. So this is fixed. And then this is basically stretching this sheet in this direction. And based on that, initially the sheet is in bulged, and then it will be stretched. What do you think this belongs to? And um, most of the students are answering A, so they're saying it belongs to tension, which I feel is true. One, a few students have answered compression, tension, compression, or bending. I don't see why. So basically, generally, we are defining forming methods corresponding to the applied stress, and the type of stress which we apply defines this category. So here we are only applying tensile stress. Here we are applying tensile, but the compression is basically the resultant in the rim, which we cannot really see here. Here we are applying compressive stress only. Um, but yeah, and again, we have already discussed the other two cases. So the case of bending and the case of shear. Okay, so if you have any questions related to these processes on why it is so, or you understood it, um, if you have any questions, you can write down in the public chat and I will be very happy to answer them on an adequate time slot. But now we move on to the next slide. So before we move forward, we need to clarify certain definitions of certain terminologies because those are the ones which we'll be using again and again throughout our subject or throughout our courses. So forming basically according to standard 8580 is manufacturing by plastically modifying the form of a body. So which means the permanent deformation of component is referred to as forming. In this process, both mass and material cohesion are maintained. So therefore, when we talk about the cutting or the permanent shearing methods, they do not fall into the category of forming. They they have a different category of shearing in the material in the hierarchy. So in the process of forming, mass and material cohesion are maintained. Just remember that. And the goals of forming are generally to geometrically deform the material into a desired shape, change the material characteristics by strain hardening or by strain hardening or changing its shape or something like that, or changing the surface properties or texture by going through a certain process of permanent deformation. And then formability is basically the characteristic of the material which is being processed under the influence of external force or moments to change its shape without losing its inner connection. So formability is basically um, I will write here material property, um, whereas forming is basically the process condition. And then we talk about flow stress, which is basically the required external stress here it is written in bracket true, which is a kind of a stress to achieve and maintain plastic flow under uniaxial stress conditions of the material. So this is something which we will look into more detail, but just remember that material deforms plastically under when we apply the stress which is more than um, the when we apply flow stress. So the condition of flow stress has to be fulfilled for the material to undergo plastic deformation, and that is something which we will cover in the next slides now. And then we have a deformed zone, which is the specially limited part of the workpiece volume, which is in relevant movement in the plastic state. So the area of the material which undergoes plastic deformation is called deformed zone. Now the classification of forming processes can be done based on the main loadings, like we have seen in the previous slide, which is compression, tension, bending, and shear forming. They can also be classified based on temperatures, so hot, warm, or cold. Um, so depending on these three conditions, the material formability, so the ability of the material to form changes, and therefore they can also be categorized based on temperatures. They can also be categorized based on the action force, which is direct or indirect. And they can also be categorized based on the shape change. So is it converting the shape into a sheet, a thin, um, um, a, a thin shape, or a massive forming, which is a complex shape. Um, so it can also be classified depending on the shape constraint. So if during forming, was it partially constrained or was it completely constrained? And this usually falls within the category of forging, where the material can be partially or fully constrained. And then they can be classified based on the movement of the form part. So was there a straight movement or a helical movement? So single axis or two axis movements. And then it can also be classified based on the conditions in the forming zone. So were the conditions in the forming zone stationary or non-stationary? Yeah. um, I have to change this. Oh, yeah. Okay. Um, so yeah, then based on the general backgrounds, now we know that how they can be classified. So I would like to just quickly touch or brush up the previous knowledge, or as we saw the last time, that many of the students here have not yet uh, took part in the fundamentals of fluxus information course. So I thought that it would be a good idea to just include some slides on the material flow conditions and yield criterias, and to just brush up that knowledge. This is something which probably you would have studied in your previous courses, but here we are just touching it up quickly to uh, because we will be using this quite many times in this course. So yeah, um, for an isotropic material, the flow condition depends only on the main stresses, which are sigma 1, sigma 2, sigma 3. So the principal stresses in x direction and y direction and z direction. And yield criteria is a function of these three main stresses. However, only the deviatoric stresses are effective for plastic deformation. So um, when the deviatoric stress is basically higher than this is higher than this yield surface, only then the material will start to plastically deform. Um, um, F here is an area in the Cartesian coordinate system, and every point of this area fulfills the following condition. So sigma 1 plus sigma 2 plus sigma 3, sum of all stresses is equals to 0, and then the material basically is within this, remains within this area. Um, this condition corresponds to octahedral surface in the coordinate system, which we can see here, or a more circular shape here. And the material starts to flow when the stress of the deviator reaches a certain critical value. So when the deviatoric stress, which we will look into the next slide, when that will be higher than any of these points which are mentioned in these two curves by von Mises criteria or Tresca criteria of the flow, then the material will start to flow. All the points on the octahedral surface which characterize the start of the flow are located on the so-called yield curve. So we call these a yield curve. So one is Tresca yield curve. Okay, can you hear me now? Oh, okay, okay. Sorry. Um, so yeah, I will repeat this again. Um, the stress tensor, uh, the hydrostatic stress tensor is basically when sigma 1, sigma 2, and sigma 3 all are equal to 0. And if this condition is met, it is called hydrostatic stress tensor. Which means that, for example, if we have a cube like this and we apply equal amounts of loads in all directions, for example, a cube um, under a very high pressure load from all directions, the material cannot flow in a certain direction. Um, but if the load in one direction is more than the load in other two directions, then the material tends to flow, but it has to be higher than a certain limit, and that is where this yield curve comes in. So the state described thereby is called hydrostatic stress state, um, this state, and since an incompressible body cannot undergo deformation, um, it is possible to separate the hydrostatic stress tensor from the deformation stress tensor. So we call the the mean stress by averaging the values of all these stresses. So if we have um, sigma 1 is different than sigma 2 is different than sigma 3, then we can just calculate a mean stress. So this will be this formula, which we can then subtract from all these values, and the resultant will be basically the factor which will be um, responsible for material deformation. So if we have an applied stress on a certain material which can be represented with this tensor, where sigma x is principal load in x direction, shear load in xy direction, shear load in xz direction, and then again shear load in yx, shear load in yz, principal in y direction, and then shears in z, and then principal load in z direction. We can subtract this mean from all these principal stresses, and the remainder will be basically the deviatoric stress. So the kind of stress which will be responsible for material deformation. And then this component here will basically be the hydrostatic stress tensor, which is the applied load which does not contribute towards material deformation. So this stress deviator uh, has to be more than this yield point, only then the material will flow. Okay, so there are different kinds of interactions which take place in the forming process. And based on those interactions, the forming processes can be classified um, in different categories. So, for example, they can be categorized in drawing, rolling, and extrusion because they all drawing, rolling, and extrusion fall under the same category because the similar kind of interactions take place in them. And then there is sheet metal forming where a different kind of interaction takes place. And then there is forging where again different kinds of factors are taking place. And if you look at this the classification of forming process according to this, we will see that we can divide it in three components. One is um, the material, the other is the interaction, and the third is the equipment involved. And then when we look at these three main categories which are listed here on top, we will see that drawing, rolling, and extrusion um, generally fall under the category of one process where the initial material has is of similar shape, of similar geometry. The type of loads or the dies or the interactions between the component and the workpiece are almost similar as well. And then the equipment is generally different but behaves similarly. So they are then classified in one interaction. And then sheet metal forming has a different type of material geometry, different attributes associated with it, and the interaction of the workpiece and the component is different, and therefore it falls within a different category. And forging it is completely different. So these are the classifications based on different modeling techniques, boundary conditions, and assumptions, and this is what can be shown here in this figure. Now, one of the classifications of these forming processes or material deformations is based on how we are applying the load and how we are how the material is deforming. Another type of material deformation behavior can be classified based on different scales. So here, this is a very interesting figure where we generally, when we talk about material deformations, we talk about this area here, which is the bulk deformation behavior of the material. So does it go undergo bending, does it undergo tension or compression, and how it is deforming. But we know from the fundamentals of materials and fundamentals of plastic deformation that the material on the bulk deformation behavior of the material is generally dependent on its microstructural attributes. So it's the size of the grains and the orientation of the grains and then the microstructural constituents. And then on the smaller scale, then there are different precipitates, grain boundaries, and other three-dimensional defects which affect the material deformation behavior. And when we look at them closely, so then we know that there are 2D defects in the material, which are generally edge dislocations and dipole dislocations, which generally are responsible for material deformation. And if we go further down, then we see that there are different lattice types, and based on the lattice structures, there are different glide planes and slip planes which are responsible on which the material can flow easily, and therefore the material deformation takes place. The dislocations initiate and evolve, and then the material deformation can take place. So until now, we have been looking at the possibility of material deformation and material formability on the bulk on the bulk side, but there are also different scales. For example, below the macroscopic scale, there is a mesoscale, microscale, and nanoscale at which the material deformation is also analyzed and studied, and this is something which we will also consider in our course. So not only to talk about the material modeling on the macroscopic scale, but also on the meso and microscopic scales. hmm And then how those small models work is also of interest. So I will just quickly select this slide and go here. So for example, we know that if we are interested in looking at the material behavior on the bulk, um, at the bulk, if we are interested in looking at the bulk deformation behavior of a material, the yield criteria is of interest. So we know that once the deviatoric stress will cross the yield surface, the material will deform and will behave in a certain way. But this criteria basically comes from the overall microstructural attributes of the material, and these microstructural attributes are then dependent on the elastic tensor, the phase fractions, the defect dynamics, deformation mechanics, orientations, and homogenization schemes. So the numerical simulation models are now able to capture all these attributes and look at the material behavior at a certain point, and based on that, provide us with the yield functions, which then can be used to model materials on the bulk scale. And in this course, we will try to discuss this as well. Now, just to quickly go through once we are mhm. So once we are started with this debate of different kinds of numerical simulation models, we can also mhm. It is a link on this slide. And then we can also take a look at typical approaches in the materials technology, um, which are analytical solutions at the very first. For example, when we talk about the analytical solutions, we talk about the basic description of solutions of specific problems, and analogy considerations. For example, we generally know about Hooke's law, uh, which is stress is equals to modulus of elasticity multiplied by strain. Sorry. And here, this is basically an analytical model where we have correlated the stress and strain in the material based on this constant, which is Young's modulus, and a modulus of elasticity. And from this kind of equation, we can calculate any unknowns in the system. And these models are good. They give us quite accurate results, but they do not define the material at a very local scale, or they are very specific. So we have to know all the principal methodologies of how the material is behaving or deforming to know to model these systems. And they are generally good for very simpler systems, but for complicated systems, the equations are relatively difficult to construct or to develop. And then we have a possibility of stochastic models, which are probability based functions. I'm not generally very much aware of how these kind of models are developed, but what they do is basically they are probabilistic models. So when we are changing one input, they give us a possibility of outcomes with a certain probability of how significant a process can occur or how insignificant a process can occur in a certain area. And then we have characteristic models, which are dependent on phase boundary area phenomena and microscopic solidification processes. Generally, they are about the interaction of different phases with each other on a very local scale. And then generally we also have strip models where we divide our bulk deformation process in small strips where a different function is true for that strip, but then we have to calculate the solution for each strip and then combine it together to form a whole solution. So here we only write equations for small strips, and then by dividing the area into those small strips we can then find out a solution for the whole system. And these models are generally used for forming processes and rolling force calculations. Um, then there are different general numerical methods. So these were different types of um, methods for finding out solutions. Uh, and then there are different numerical methods where basically a numerical method is where we um, um, divide a big problem into smaller pieces and then try to apply simple equations on one small piece and try to solve this system. And based on that, um, we get the desired results for that element, and then we apply it on the bulk material, and then we get solutions for that. And here we have three different types of methods. So one is finite difference method, where we generally use it for a difference in the approaches. For example, generally this type of method is used for calculating diffusion of diffusion systems. Um, it is or the conversion processes or the precipitation processes. And then we have finite volume method, which is based on um, understanding that a unit volume has a specific smaller area has a finite volume, and that volume remains unchanged. And then basically these kind of models are used to calculate flow calculations or solidification solutions, and the equilibrium um, or the convergence of the model depends on the sum of all volumes is equals to uh, a specific number. And then we have finite element method, where we divide our big problem into smaller components, where each component is called an element, and it is basically used for structural simulations or forming simulations, where we know that the sum of all forces and sum of all um, deformations is sum of all forces is equals to zero throughout the system, and sum of all moments is equal to zero throughout the system. And mm, this is basically the kind of simulation model which we will be using a lot in our work here. Before I go forward, what I want to do is before I go forward, what I want to do is I want to share a video. We will see it to a certain extent, um, and to get an idea of how finite element simulations are working. Um, are you able to listen to the video audio? Super. Okay. Okay, so you can hear me right. I hope the video was interesting and helpful. Um, Generally, you get the idea at the end of the video that what the computers are automatically doing, ideally, and what are we controlling as inputs and outputs. And that is a bigger picture which is important to understand in case of these models and understandings, so you know that when we are studying all this, where does this fit in, how does it work. And the presenter in the video just only shared some of the cases of very simplistic equations and very simplistic models. Of course, there are different approaches and different models and different methodologies, and that is something which we will um, analyze here. As he mentioned, there are also different building blocks of modeling. So there are different types of basic equations which can be applied to those smaller discretized elements to calculate different processes. And a few of them are Navier-Stokes equations for calculating the flow processes within those small elements. Then there are Fourier equations for calculating the heat conduction and temperature fields in those elements one by one, and then assembling them together. And then there are Fix's laws for diffusion processes, Maxwell equations for electromagnetic fields, thermodynamic models for state diagrams on what the phase will be and what the conditions would be, and then the kinetic approaches to kinetic reactions, such as in the blast furnaces. So once we break down our bigger problem into smaller discretized components, then we can apply these different types of equations or different types of models to calculate simplistic solutions for those small elements, and then can combine the solutions together to overall solve a bigger boundary value problem. Then the models can generally be categorized in two different categories. The static models, which we will look first. Um, so they generally deal with the initial and the final conditions of the system. And then there are dynamic models, which deal with generally the time integration or the time step evolution of the processes on uh, how we reach that certain point. So in the dynamic models, we have a time component built into the model, whereas in the static model, we only have the final condition of the system built into the model. Yeah, and then we, for example, here take a look at a specific example of um, a rolling pilot plant um, where we are heating our material in an inductive furnace, and then we are roughing our material. We are Yeah, so we are heating up our material initially to a desired temperature. Then we are roughing it up um, through the roughing stand, and then removing all the scales and everything. And then the drivers, these then push the material into the rolling trains, where the material is rolled to the desired shape, and then it is coiled into um, to form a coil after cooling. And later, if we want to do a heat treatment process, we have a dedicated furnace where this can be done. And if we have certain conditions of output material, so we want the material to have these attributes, we can define these boundary conditions using a numerical simulation method, and what we get is basically an outcome of how um, um, so what will be the different temperatures at different points of the material. So this is a kind of information which is quite hard to get from the experimental setups. So what is the temperature condition on every point of the material? But it is quite easy to solve the numerical simulation equations for this whole process to define what are the initial conditions, what are the final conditions, and how the process is being carried out to basically calculate the different temperatures in different regimes, as well as different grain sizes. So depending on the model which we have defined. Oh, it should be working. Why isn't it? Ah, yes. And then, for example, here we can see that again, this is basically the temperature, and this is the grain size graph, where we see that the grain size is quite large here before rolling, and then after rolling the grain size is basically reduced to um, is relatively reduced to quite small, where it is small, but due to a certain time constraint it is then growing again after the rolling process. And then we see that generally in the end we have a grain size of almost around 30 micrometers, and here we see the different temperature fluctuations along the model. So this is basically the kind of output which we get from our numerical simulation models, and then this can be processed to basically optimize the parameters, or basically look at how we need to change our process to change our desired outcomes, or if we fix our process parameters, then what will be our desired outcomes before actually doing this. um, so again, I will come back to this very um, um, interesting data flow of the materials, and this is something which we already discussed in the previous lecture, but here we will section it down into different components. On initially we have a preprocessor. So this is basically what is being controlled by um, the user, where we define the geometrical parameters. um, what is this? uh, oh, why is it not working? Oh, okay, okay. Okay, so the pointer is not working. I don't know why, but in the preprocessor we have our geometrical parameters, which are generally tool geometry and workpiece geometry. Our process parameters on the motion of the die, the temperatures, lubrications, and material conditions, and then we have our material parameters on how the material behaves under different loading conditions. Is it isotropic and isotropic, and at what different temperatures how the material behaves, and these are all the inputs which we define in the preprocessor of the simulation model, and this is basically controlled by the user. And then we have another factor of boundary conditions, which has different conditions related to the restriction of the motions, and there are several assumptions which we take during our process. So, what are the temperature limitations? What are the initial temperatures? What are the final temperatures? How the material will undergo a certain deformation process? How a die, which uh, motions a die can undergo and which it cannot, and things like this. And this is what we do, which are also undertaken by the user. And then all this information is basically fed into the computer system, which compiles it into the desired information of and which compiles it into a solver, and then runs all these equations and gives us the output. And then those outputs are basically then again processed by the user to get the desired to, to see if the optimal results are obtained or something needs to be. Yeah, and these are parts of the numerical simulation model which will be covered during this course. And in the next few lectures, you will basically be looking at the different solvers, different boundary conditions, and then different material models and their parameters on how they are defined, what are their types, and how we do it, and how this can be done to obtain the desired results. So yeah, so in this lecture, what we have done is we have covered the background of metal forming. We have covered the classification of different types of forming processes. We covered the quick connection with the fundamentals of process deformation course and how the materials undergo different deformations. And then we looked into the basic material models and numerical solution possibilities. Um, then we obtained information. Then we saw that how the information can be obtained from the numerical simulations um, in the form of numerical data or represented on pictorially or in a graphical format. And then we took a look into the components of the numerical simulation model, which will further be explained in the upcoming lectures. So yeah, that was it from my side. So if you have any questions, please feel free to ask. Um, Again, I will try to upload the recording of this lecture soon on the portal, and we'll share the link with everyone. Um, Meanwhile, just keep an eye on the emails and the messages so I may write something. Um, I will again upload the slides of this lecture on the portal, and yeah. So that was it from my side. If you do not have any questions, then we can leave. Um, what would be the format of the final exam? It is a pen and paper type exam, and that's all I can say. We are not sure if it will be online or if it will be offline, face to face or um, online. But that's all I can say for now. So the recordings will be on Opal. The recordings will be on the given link which is provided. So if you will look here, so it is written here, the lectures will also be available on this link. And this is something which I stated in the beginning of the lecture, that I have not been able to get access to this portal and upload the lectures. But of course in the future I will do that.